All right, starting with my talk. Well, memory allocation, kind of important. I hope you all agree. And symbolic execution, that's why we're here. So sounds nice so far. But why are we talking about this? I thought memory allocation, I know, had been, not solved, but pretty much done. Well, going back to symbolic execution, right? I'm not going to go through this example in this conference, right? I mean, if anybody has a question, please ask, but otherwise, awesome. So we've got a state, and that state forks at the if, right? Now we've got a new path condition that now says that our lambda must be equal to 0 to hit that bug. Or we've got the other fork state where we say the lambda is not equal to 0. So far, so good. Memory allocation works. We've got variables. Everything's fine, right? All right. So what's the address of x? Now, at this point, I'm going to take a very specific approach to KLEE, but in general, there's a bunch of symbolic execution engines that work similar. Of course, there are symbolic execution engines that work completely different. Now, in KLEE, we've got the KLEE process, and we've got the states in there, right? And then we've got some bytes somewhere, and they have an address. That is basically where we get our address, right? So we've got a buffer in KLEE that has an address, and this is the address that we're going to use when we allocate bytes in the program on test. Memory object states should ring a bell. And in between, we've got this mapping, right? So the state refers to the value, which then refers to this buffer, which we use for its address at this point. And when we fork, we're very happy because we have copy on write. So our new state 1 prime refers to the same value object and still refers to the same buffer. Now, if we change that value, copy on write happens, right? The on write part of the copy of the on write part, more importantly. And maybe we have a -1 in state 1 prime and a 0 in state 1, and they still refer to the same address. Again, so far, so good. We've got a variable that hasn't randomly changed its address. Great. Now, what happens, however, if state 2, let's say we forked that earlier from state 1, now wants to also allocate its x? Because, I mean, it just got there, right? Well, it needs to allocate one of these buffers. And since we use these buffers for external function calls, these are actual system-level buffers in the KLEE process. Oops. Now we've got two variables x, which from my naive point of view are the exact freaking same variable x, except they cannot have the same address. Because they're not the result of a fork, but they've been allocated after that fork. And therefore, I need to have two of those external function call buffers, which by definition cannot have the same address because they're objects in the KLEE process, right? And this is where the whole question with deterministic memory allocation becomes interesting in KLEE.
Daniel, is this a problem because you're wasting memory, you're not using that memory, or is it a problem because you're going to run into problems with points comparisons?
The problem is that we do not know whether state 2 has a virtual address layout where the address OXZ is available. So we cannot know if we could have used that address.
The states, but from a correctness of KLEE point of view, states 1 and 2 in some sense exist in different universes. Is that correct?
They should, but they don't, because if state 1 had not existed, we would have gotten a different address in state 2. We could have gotten the OXZ beef address.
Which matters if your program is going to ask questions like, what's the absolute value of this address? There are a few things where this actually matters. We've actually evaluated that. The big one is actually stuff like comparisons for equality and order in the address space, which is relevant, for example, memmove. But we'll get to that again. I've got an example with memmove at the very end, so don't get to it. So the big point here is that suddenly we've got two states, and what we do in one state impacts what we get in the other state. And that is definitely not what we want. Of course, bonus feature, since we're just using malloc here, if we run KLEE again, we will obviously get a different result because malloc is not deterministic. And if we change the searcher, we might be executing state 2 first and therefore swap the addresses, right? So there's a bunch of things how this gets unstable, this construct. Of course, in any case, we will end up with a variable x and write to it, and we can do external function calls with it. Right, so this is not everything is horribly broken, just a bit broken. So why do we care? Right, this gets kind of back to Ali's question. Well, the obvious thing is we want to have repeatable experiments. If I run something and then I go to Christian in his office and tell him, oh look, I found a bug, and Christian runs it and doesn't find it, I look really stupid. Well, however, there's also something more interesting, and that is if we do more advanced techniques than just, oh, look, I found a bug, we actually do need deterministic execution. One example for that was a partial order execution technique that I did, where we basically went ahead and tried to figure out if two events in our partial order are equivalent. But they can only be equivalent if they're actually the same, not kind of sort of similar. So we need to compute exact equality, and we cannot get exact equality if we cannot get the same address again. And if we cannot make that guarantee, the whole theory becomes unsound, which is kind of not cool. Another work where we also need something similar is work where the idea was to find repeating memory states and then to detect that if we are in an infinite loop. Now, of course, if we don't have a deterministic memory allocator, and in fact, maybe we're forking, we can actually construct cases where with the KLEE's default memory allocator, you will be unable to detect that you're in a loop because due to the interference of this state with its own forks, you will never be in a loop. You will always guaranteed get a different memory address. Which, well, technically, so we're not doing something wrong, it's just not very helpful, right? Because like we're kind of preventing ourselves from finding a loop by adding interference that prevents the loop from existing until the 64 iterations.
Are you saying that's false negative? You're creating false negative.
Well, technically, we will find it in 2 to the 64 iterations, which brings us back to the whole everything is finite argument. Ignoring that stupid argument because
when you say where I find a new address every time, which malloc doesn't do, then that will lead to
yes, the technique does have false negatives, to be very clear, because we're doing termination analysis, right? You could argue that it's a valid implementation of malloc to always return a different address. It's not an invalid implementation of malloc. It's just not a very smart one. So, right, you could build a malloc that has this exact behavior in practice, but why would you?
I just need you'll miss funds that actually occur.
Yes, yes, yes. And finally, one cool example is Merkley, where the idea was to basically memorize the symbolic execution to be able to stop it and restart it. And of course, if we want to stop and restart stuff, it helps if we actually end up with the same memory after restarting, right? Deterministic being useful for restarting stuff. All right, so how do you do that? Well, the idea is very simple. Let's not use any of the fancy pan system allocators. Let's build an allocator for symbolic execution. Important properties. And I'd like really to point this out because you guys can actually appreciate this. We spend a bit of time trying to figure out what actually do we want from an allocator like this. Well, the first thing is we can't break external function calls because although I personally hate the whole mechanism, every time I talk to someone about KLEE who's not like one of the core, I build stuff with KLEE people, the thing that they always point out is, yeah, but it can do external function calls. Like, yes, okay, we're not going to break it. Then if we run it twice, we want to have the same result, like the most basic definition of determinism. We call that cross run, right? So across 2 runs, same results. A bit more specific here, we also want to have cross path determinism. So you remember our example in the beginning where we had 2 paths through that program, but they were basically the same. but since they all existed at the same time, they were influencing one another. What we want is that if we have one path, it doesn't know anything and it doesn't get influenced by any other path that you might also be having in your execution engine. Then something useful for KLEE specific was similar techniques are used widely in the whole memory testing area. We want to make sure that if we misindex an array, the whole thing traps, right? So we can't have two objects right next to another. So off by one error, it's actually unallocated memory and not the next object. In generally speaking, we want them to be as far away from another as possible. Similarly, we want them to be temporarily distant. Why? Use after free. If my use after free is valid, because I've already got a new object there, I don't detect it, and I want KLEE to detect errors. And finally, something that is really a kind of very soft goal. Ideally, our allocator does not have a property such that if I allocate like 1 byte, everything changes compared to not allocating that byte. Or even worse, I hit an if, and I allocate a temporary object, remove it again, and exit that if, then it should have behaving as if that object never existed, maybe. So the general architecture of the whole thing. We mmap one large region and attach forkable metadata to the initial state. We use that region to provide addresses and only for external function calls otherwise, because KLEE already stores object data in the states. Then we categorize allocations to reduce the snowball effect. We have multiple allocators to disconnect the second heap, and the whole thing looks like this. As you can see, we have 4 different allocators, and they bin by allocation size. So if you put a 256 byte object on the stack, it goes right here. Why is that important? Because now you've sort of mixed up that one bin, but everything else remains the same. An interesting thing in this figure is, by the way, this number, 1 terabyte of virtual address space. That is actually the default number that we use. Remember, virtual address space is not actually expensive, but it gives us room to play around. So how do we do the spatial distancing? Well, for the sized bins, that is everything that is not like bigger than 4K, imagine we just divide it up into slots of the equal size. Then we stick the first one right in the middle. Middle sounds good. And then we basically always half. So easy so far, right? And of course, if one gets deallocated, we can reuse that and we won't go further into the halving without necessary. The large object bins basically work the same, but with a more dynamic data structure, because stuff gets more dynamic when you have like everything from 4K to 2 to the 64. Now, does it actually work? Well, you can see our memory consumption here. We did a study. On the left-hand side, you can see the whole thing with DFS. On the right-hand side with Rankov. As you can see, it actually differs between the two, but you can also see that basically memory consumption doesn't change a lot, which is good because we're kind of doing a whole lot more of storing, but we did a whole lot of copy on write. Seems to work out very nice. But then you look at performance, and suddenly we're like really good. If you can see up here, that's the biggest one. We suddenly have a massive performance improvement. We spent some time theorizing why that is, and the biggest hint is if you look at the solver time, and then I'll just flip back and forth between those slides. I hope I don't need to say a lot about that. So it turns out we actually generate much easier constraints for the solver. Similar, we can see that locally, when we run stuff again, we can see where it diverges from what we did in the first time. And as you can see, it goes down, for example, from 22 to 12 in this example. So we actually hit our goal of having fewer divergent code paths. Those that remain are typically stuff like looking at system time, right? Something that has nothing to do with memory and everything to do with that we're not modeling all function calls in KLEE, and then an external function call happens to the file system or time or something like that. We have not found any issue related to memory in the ones that we look at.
And now the promised example for Ellie. This is actually memmove, the implementation that is used in KLEE usilipc. And you don't need to read it. You just need to see this one highlighted part where we compare the destination pointer with the source pointer. The reason for that is that memmove may copy overlapping areas, and depending on which way you overlap, you need to go front to back or back to front. And this means that suddenly we have two arbitrary basically pointers that are compared for ordering in the address space. And yes, you will be moving memmove, even if you don't recall it right now. Yeah, so memory layout changes. That's the whole point of determinism, like having not change randomly. And memmove is a problem here. To summarize the whole thing. One, we found that the memory allocator actually does have significant impact on symbolic execution. Two, we implemented KDalloc in KLEE, and we've shown performance and memory consumption are not impacted significantly negatively. Right? There are, of course, you can find examples where it's worse, you can find examples where it's better. So you saw the graphs, but it's basically on a line, except for the case where we are massively better. Use after free detection is improved. I have not talked about this. Basically, we just do a quarantine, right? So you can pick a parameter that says how soon should reuse happen. Depending on your use case, you may put it to infinity, or you may put it to 1 or 0, your choice. And we actually have specific benefits for a bunch of symbolic execution techniques that I talked about earlier. All of these actually work better with our mechanic. In the first two cases where I talked about, they were fundamentally required or fundamentally an improvement. In the third case, we could see that empirical improvement a minute ago. And finally, yes, KDalloc is becoming part of mainline KLEE. I'm really sad. I was hoping to tell you that KDalloc is part of mainline KLEE, but I forgot who it was, but we heard something about CI already, right? So yeah, that was my talk.